In this video, we're going to look at another example of areas between curves. So here we're finding the area of the region bounded by the curves y is equal to x cubed minus x. This is a cubic function, it's a polynomial, and y is equal to sine of pi x, and this is a trig function, it's a sine function. X equals 0, x equals 2. Step 1 is to find the intersection points of y is equal to x cubed minus x and y is equal to sine of pi x. To do this, we let y equals y and solve for x. However, we can't use algebra to solve this. That's not going to help us. So what we have to do is we have to kind of analyze this or guess at values of x that make these two expressions equal to each other. The first thing we will notice is we can kind of find the x-intercepts of each of them, and we'll find out that their x-intercepts are exactly the same, and hence those are the intersection points. So let's look at x cubed minus x first. So here we have x cubed minus x. Let's factorize this. We get x times, factorizing x times x squared minus 1. That's difference of squares. Let's factorize that further, and we get x minus 1 times x plus 1. And that's y equals x cubed minus x. If we make this equal to 0 and solve for x, we're going to get x equals 0. We're going to get x minus 1 equals 0, which gives us x equals 1. And if we make x plus 1 equals 0, we'll get x equals negative 1. So what we have is x equals 0, x equals 1, and x equals negative 1. And of course, y equals 0. And these are the x-intercepts of the function y equals x cubed minus x. Now, you will also notice that y equals sine pi x has exactly the same x-intercepts. So if we put x equals 0 into this expression, we get y is equal to sine of 0, which is just 0. And if we put x equals 1, we get y is equal to sine of pi, and sine of pi, sine of any multiple of pi, is 0. And if we put x equals negative 1, we get y is equal to sine of minus pi, and that's also 0. So these two functions share exactly the same x-intercepts. Those are the intersection points. So what we notice is that y equals x cubed minus x and y is equal to sine of pi x both share the same x-intercepts. Those intercepts are x equals negative 1, x equals 0, and x equals 1. I'm going to review what we did before. Y is equal to x cubed minus x. We factorize the x times x squared minus 1. X times factorize the difference of squares, that's x minus 1 times x plus 1 equals 0. And that gave us the x-intercepts as x equals negative 1, x equals 0, and x equals 1. And y is equal to sine of pi x. We make this equal to 0. And we got x equals negative 1, x equals 0, and x equals 1. Exactly the same x-intercepts for both functions. That's the key here. So the points of intersection of the two are x equals negative 1. How do we get the y value? We can put it into either function. I can put it into y equals sine of pi x. We get y equals 0, x equals 0, y is equal to, I can put x equals 0 in either function. I'll put it into this one, 0 cubed minus 0, that's just 0, and x equals 1. Put x equals 1 into the sine function, we get y is sine of pi, which is 0. These are the intersection points. So the intersection points are negative 1, 0, xy coordinates, 0, 0, and 1, 0. All right, step 2 is to sketch a bounded region, y is equal to x cubed minus x, and y is equal to sine of pi x. X equals 0 and x equals 2. We have that sketched here. That's a fairly easy plot. We have y equals x cubed minus x and y equals sine of pi x, and they're going through the intersection points negative 1, 0, and 1. So when we try to solve for the area, we basically have to split up the integral into two separate regions. We integrate from 0 to 1, the top function minus the bottom function. The top function is sine of pi x. The bottom function is the cubic function, x cubed minus x. It's always going to be y top minus y bottom. It's always more minus less. That's key concept. Now, to the right of x equals 1, the cubic function is on top. The top point of the rectangle touches the curve y equals x cubed minus x. And the bottom part of the rectangle touches the curve y equals sine of pi x. So we have to add plus integral from 1 to 2. And now the top function is a cubic function, x cubed minus x. And the bottom function is the sine function, sine of pi x. And all integrated with respect to x. We're going to formalize that in the next step. All right, so we want to set up a definite integral to find the area, the points of intersection. We found those to be the x-coordinates of the point of intersection, or x equals -1, x equals 0, and x equals 1. Now you will notice that sine of pi x, the sine function, is larger than x cubed minus x when x is between 1 and 0. We can see that from the diagram. When x is between 0 and 1, the sine function is on top and the cubic function is at the bottom. All right. And similarly, when an x cubed minus x is larger, the cubic function is larger than the sine function, sine of pi x, when x is between 2 and 1. So the area of the bounded region is, we split it up into two separate definite integrals. Area is integral from 0 to 1. The top function is sine of pi x, minus the bottom function is a cubic function, x cubed minus x dx. Plus, now from integral from 1 to 2, and now it's going to just switch. It's going to be the opposite. The top function is a cubic function, x cubed minus x. The bottom function is the sine function, sine of pi x. And these are easy integrals to solve. So we have drawn two rectangles here. So this is y top minus y bottom in the interval x between 0 and 1. And here we have y top minus y bottom in the interval between 1 to 2. All right, so now we have to solve this. We have area is equal to integral from 0 to 1 sine pi x minus x cubed minus x dx. That's the integral from 0 to 1. And from 1 to 2, the cubic function is the top function. That's x cubed minus x minus sine pi x. That's the bottom function. So to solve this, we're going to look at the first integral because that involves U substitution. So let U be equal to pi x du. Differentiate both sides, we get pi dx. And we have integral from 0 to 1 sine of pi x dx. Let me find the general antiderivative without the limits, just so we have the antiderivative. So that's going to be integral sine of u, and dx is 1 over pi du. When we integrate this, we get negative 1 over pi cosine of u, and u is pi x plus c. So that's the antiderivative. Area is equal to integral sine of pi x. Let's actually split up these integrals. It's easier to solve them. So integral from 0 to 1 sine of pi x dx minus integral from 0 to 1 x cubed minus x dx plus integral from 1 to 2 x cubed minus x dx minus integral from 1 to 2 sine of pi x dx. All right, so what we have is for the first integral, we already solved that. Integral sine of pi x is negative 1 over pi cosine of pi x evaluated from 0 to 1 minus integral of x cubed minus x, that's just reversing the power rule, that's going to be x to the fourth over 4 minus x squared over 2, evaluated from 0 to 1, plus integral from 1 to 2, that's going to be x to the fourth over 4. Antiderivative of x cubed is x to the fourth over 4 minus x squared over 2, evaluated from 1 to 2, minus integral sine pi x, and we found that to be negative 1 over pi, so that's plus 1 over pi cosine of pi x from 1 to 2, evaluated from 1 to 2. Now we have to substitute this in. So we get area is equal to negative 1 over pi times cos of pi, so let me put cos of pi here, minus cos of 0, minus 1/4, minus 1/2, minus, put 0 in, it's just going to be 0 minus 0, plus, and we have 2 to the 4, that's 16 over 4, that's 4, minus 2 squared, 4 over 2, that's 2, minus, put 1 in, we get 1/4, minus 1/2, plus 1 over pi, times cos of 2 pi, minus cos of pi. Okay, now we have to evaluate all of this. So let's rewrite this on the next page. Area is equal to minus, let me look at the last page. So we have area is negative 1 over pi. Area is equal to negative 1 over pi times cosine pi minus cos of 0. Let's take a look at that again. That's cos pi minus cos 0. Cos pi minus cos 0. And we have minus 1/4 minus 1/2. Minus 1/4 minus 1/2. Plus 2 minus 1/4 minus 1/2. Plus 2 minus 1/4 minus 1/2. Plus 1 over pi times cosine 2 pi minus cos pi, plus 1 over pi times cosine 2 pi minus cosine pi. Let's double check to see we haven't made any mistakes. So we have negative 1 over pi times cos pi minus cos 0 minus 1/4 minus 1/2 plus 4 minus 2, that's 2 minus 1/4 minus 1/2 plus 1 over pi times cos 2 pi minus cos pi. Okay, let's evaluate this. What is cosine of pi? Cos of pi, cos of 180, that is negative 1. Cos of 0 is 1. And cos of 2 pi, cos of 360 is 1. Cos of pi is negative 1. We do this very carefully. Area is equal to negative 1 over pi times negative 1 minus 1 is minus 2 minus 1/4 minus 1/2, that's 1/4 minus 2/4, that's negative 1/4, plus 2 minus 1/4 minus 1/2, that's 1/4 minus 2/4, that's negative 1/4 again, plus 1 over pi, times cos of 2 pi is 1, minus 1 is 2. Very easy to make mistakes. You've got to do this really carefully. So the double negative, negative 1 over pi times negative 2, that's 2 over pi, double negative again, plus 1/4, plus 2, minus is plus, double negative is 1/4, plus 2 over pi. So we got 2 over pi plus 2 over pi, that's going to add up to 4 over pi. We got 1/4 plus 1/4, that's going to add up to 1/2, plus 2. If you decimalize this, that's going to give us 3.77. This is the shaded region. Let's show that on the previous page. This is the shaded region right here. So that's basically all of this. This area plus this area. The tricky part is setting up the two separate integrals on the two separate intervals. And the reason, of course, is because to the left of the intersection point, the top function is a sine function, the bottom function is the cubic function x cubed minus x, and to the right of the intersection point from x equals 1 to x equals 2, the top function is the cubic function x cubed minus x, and the bottom function is the sine function sine of pi x. All right, thanks.